Okay, our last section, section 5.4, really what it's about is linear regressions, and we'll leave that. So a linear regression, they can also use the term linear trend line interchangeably. So given a scatter plot of data points, and I'll show you what they mean by that. There's just an example of a scatter plot of data points. The line was created by Excel. It's the line of best fit. It's called a trend line or a linear regression line. But here's the actual data points. So given a scatter plot of data point, an estimated line through the data which captures the overall trend. So there's the data line that captures the overall trend as done by Excel or done by a computer. So that's one way of doing it, and that's right there. Use a computer program like Excel. The other way we can do it, we can simply draw a line by hand which runs through the middle of the points. And another way we can do it is you can select two data points that seem to capture the trend and then mathematically create the line for them. Because the fact is, in the real world, you don't get perfect lines. You get data like this. Sometimes it's all over the place. Oh yeah, now we're going to note how Excel chose this line. And it chose this line, and look at the y-intercept, negative 4e plus 7. That means move the decimal after the 4 or 7 places, and it's a negative number. Now, why is it a negative number? Well, it's a negative number because the data, there's no zero. The zero, year 0 is way down here, the birth of Christ. So most of the time we would do this in a different way, so we don't have that kind of irrelevant data here. It makes no sense. And just as an example, the y-intercept, negative 40 million, which is what that is, makes no sense. We include it here to show how Excel rounds off large numbers when displaying equations. And a reminder to you to use the units of years since a certain year. And I'm going to explain that next. I started this. This is the actual data that was put in Excel in one column, and then the outlays, right? The years, the input, the amount spent on Social Security, the output. Now, this is how you would probably do it. You do years since 1975, so you'd start with 1975 being year 0. That would make 1980 year 5, 1985 year 10, 1990 would be year 15, 1995 year 20, etc., all the way down. And you would use this column and this column and state that the year 1975 equals year 0. And that avoids getting this weird y-intercept. Now we're going to take, and I'm going to show you this one, we're going to take the first and last data points, but we're still going to use 1975 and 2017, not year 0 and whatever year that would be, 25 plus 17, 42 or something. But we will. But we're just going to do a simple equation here and then interpret the rate. And we're not going to do it. I'm going to post it up for you here. So really the only thing that we're doing here is we're just doing the rate and interpreting the rate. And the rate won't change no matter what, because this number here on the bottom, if 1975 was year 0, that would be year 42. So it doesn't matter if we use this for the rate. The rate's going to be not changed that way. So we're using this data point here, the last and the first data point. And hopefully you know by now that the rate is the outputs, the change in the outputs, which is dollars in Social Security, divided by the change in the input, which is years. So dollars of Social Security per year, dollars of Social Security per year. So Social Security outlays have been increasing since 1975 at a rate of 20,957.6 millions per year. So that is the rate of change. This is the slope. So now we're going to draw a line between the same data set, draw a line between the first and the last data points. And so I can do that by, see if I can pull this off here. First and the last data points. And shape outline. Weight to that. So there's our line. Now what we're going to do is construct the equation for the line. We're going to compute an equation for the line, y being the output, millions of dollars Social Security, equals the rate of change, which is the amount of Social Security is increasing each year, plus the starting value. And the starting value is going to be 1975, year zero. Okay, so now how do we do this? Well, the first thing we're going to do is find the slope, but the slope's going to be the same as we just found up there. But let's redo the slope. So I have the data set here. We're going to take that. And I'm going to take the other one. And I'll do that on pause. So there's our first and last data point. That represents 1975 equals year zero, and you should probably always put that up. So now I'm going to do the slope, which is y2 minus y1 over x2 minus x1. So I'm going to put that down here and calculate it. You might want to put it on pause so you can do it. So there is calculation of our slope, which I said isn't any different than the way we did it above. It's the y-intercept that's going to be different. And so how would we interpret this? Is that the average yearly increase in Social Security is 20,957.6 million per year. You could say the average yearly increase in Social Security is the average 42-year increase in Social Security is that, but this is a way to put it over one. And now we can just, we're almost done with our line. Do I have to use one of these 2 points and put it in and do all that nonsense? And the answer is you should say, and I'll put the line up here and then we'll discuss that. So there's the line, and I really didn't do any math. This is the math I needed to do. Where did I get that from, and what does it mean? There's the y-intercept, the initial value. What does it mean? Well, in this case, it means that the government spent $64,658 million in year zero, which is 1975. So doing it this way makes a lot more sense.